Okay, so this is a good example of a test four. There's a little bit of conversions in the beginning, balancing equations, stoichiometry problems, and it's very focused. No electronic configuration, no naming, nothing. Just focused on stoichiometry. So if some of you were challenged with that kind of all over the place approach, you should be pleased with this test. And in fact, the next test as well. Okay, so I'm going to go through this. What is a limiting reactant or limiting reagent? Now you'll see the questions reagent and reactant are interchanged all the time. So just get used to saying one or the other. The key is limiting. Like yesterday, they talked about bicycles. We had so many wheels to so many frames, so many bicycles can you make? And coming to find out the wheels were limiting the amount of bicycles produced. So a limiting reagents Okay, so limits the amount of product. There's only one limiting reactant. Now, if I give you 5 givens, only one of them is a limiting reactant. If I give you 2, only one is. It's always one. It's also totally consumed, 100%. So what's in excess, only a percentage of it is consumed. That's step 3 when we go through that calculation. Okay, how many molecules of gaseous water are there in 23.0 times 10 squared grams of water? And we're never asked how many. Think of Avogadro's number. Okay, so we set up the given is 23. So first step, convert to moles. Now we go from moles to Avogadro's number. And we've got 3 sig figs across the board there. So I said gaseous water. Okay, notice the 22.4 didn't come into play because I didn't mention liters. I said grams. So the 22.4, even though it's a gas, doesn't come into play. So we convert to moles because we start with grams. You can always get to moles if we start with grams. Then from there, we went and converted the moles into number of particles. Okay, how many liters of gaseous water? Again, gaseous water at STP are there in so many molecules of water. So the given is 287. I want to convert that to moles. And for moles, we want to get to liters. So molecules cancel, moles cancel, left with liters. Now that's unit 3 stuff, except for the first problem. All this is unit 3 stuff. Okay, balance following equations. Hydrogen gas, what's the formula for hydrogen gas? H2. Remember, there are 7 diatonics: hydrogen gas, oxygen gas, nitrogen gas, and the halogens. Those are all diatonic, meaning they come in pairs only. So if you see the word in your next class, sometimes they'll just say hydrogen. Hydrogen doesn't exist by itself. It has to be coupled with something. Unless it's an ion, even then it's coupled with water. Okay, so we have hydrogen plus oxygen gas reacts to give water. Now the word reacts means automatically arrow, because we're talking about products now. Okay, is this balanced? No. We need 2 waters to get the oxygens up to 2, and that makes 4 hydrogens. So we did an inventory, we'd have 4 H's, 2 O's, 4 H's, 2 O's. Okay, C818. That's what is mostly in gasoline. It's called octane. You've probably heard the term octane when it's referred to gasoline. There are 3 levels of gasoline, depending on how much octane the gasoline is rated at. And most of the time, you can use the regular old, the cheapest one. unless your car specifically says premium. If it says that, there will be a difference in performance in your car. If it doesn't say that, it's a waste of money to put premium in. My late wife used to always put premium in her Cadillac. She says it runs better. No, it doesn't. If you look at the owner's manual, it just doesn't say anything about class of gasoline. So she would go to a Chevron station when the gas is more expensive there yet, and she put premium in her car. And I was like, okay, so let's balance this guy. Okay, all right, we've got 8 carbons on the left, 8 carbons on the right, 18 hydrogens on the left, it's interesting. This is a different version of OneNote came up. Okay, so we need, all right, now the oxygens, we've got 9 and 16. That's 25 on the right. So on the left, oxygens come in twos. So that means we have to have a fraction. So that's going to be 25 over 2, which gives us 25. Okay, it's balanced, but we have a fraction, so we need to clear the fraction. And most of the time, when you clear fractions, it's going to be multiplying everything by 2. Sometimes it's 3. 99% of the time, it's clearing it. It's usually 2. So that means that's a 2. This becomes 25. $18, 16. Okay. So fractions are okay. When you get to your next chemistry class, they're going to approach this differently. I've seen it being taught really poorly in terms of handling fractions. Some people say if you have to use a fraction, multiply something by 2. Okay, I take the approach, use fractions, make sure it's balanced, and then just clear them at the end. Okay. What's the purpose of balancing an equation? Remember in stoichiometry, that middle step comes from the balanced equation. So if you don't have a balanced equation, the middle step, you can't do. So the purpose of balancing an equation is so creating a molar relationship between reactants and products. Now, it could be 1, 1, 1, 1. That's fine. But you have to verify that 1, 1, 1 is in fact balanced or not. What information can be obtained is So the information is the molar relationship. That's the middle step of the stoichiometry problems. Okay, iron is made in a blast furnace using the following reaction. Carbon monoxide plus rust equals iron plus carbon dioxide. Now, if you've never seen a blast furnace, they're wild. They are truly wild, especially when you get into the big steel blast furnace. They're huge and they have molten iron bubbling in these big cauldrons. It's wild. Very unhealthy place to work. Very. Most people get asthma from working in there and typically follows with cancer. Not a nice place to work. Okay, so first things first. Let's and I need more room to work this problem. Okay. Okay. First thing first, we need to balance the thing. So let's write it bigger. Okay, so we have one carbon on the left, one on the right, two irons, well, four oxygens, two oxygens, two irons, one iron. Okay, so it's definitely not balanced. Okay, so let's balance the oxygens first. Okay, if we put a 2 here, that's going to change this to a 4. That becomes a 2. Now we have problem with carbons. So this needs to be a 2 there. That changes our oxygens to 5. So the iron's going to be easy to balance at the end. So how can we work this out? Kind of going in a spiral right now. Who wants to jump in? Yeah. Put a 3 where? On the right? So a 3 over here too. Okay, so let's take an inventory really fast and see where we are. Okay, so we have 3 and 3 on carbons. We've got 6 oxygens, 6 oxygens. And we have 2 irons, 2 irons. Okay, now notice first thing, so we have two givens. So step one is balance equation. We have two givens. Whenever we have two givens, we have to determine in two steps which limits the reaction. Okay, so let's start with CO. Okay, so we have 20 grams of CO. Okay, next step is to convert to moles. So CO is one carbon at 1201, one oxygen at 16. So that's 2801. Okay, now we're in moles. Now we're going to invoke the balanced equation to go from CO to iron. Okay, and that's 2 to 3. And again, that's why we're balancing the equation, is for that middle step. And then iron is, how much is iron? $55.85. Okay, this will tell us how much iron we made. Okay, so using carbon monoxide as the first given, that's how much iron we've made. Now we're going to do rust. Now this particular test was given over last spring, and we had more time for tests. That's why I have a limiting reactant problem during the in-class tests. You're going to get a problem like this at home, though, so you'll have more time to do it. Okay, let's see. Iron, we have 55, 85 twice. We have Okay, so we're looking at 26 versus 9. So which is limiting the reactant? The rust or carbon monoxide? Rust, because it's smaller product. Okay. All right. So that means CO is in excess. Okay, so step 3 is to find out. Now remember, the limiting reactant is totally used up, 100%. So that means there's none left. But we have excess of the other. So we need to find out how much of the other we have left over. That's step 3. So we start with the limiting reagent. Okay, that'll give us moles of rust. We want to know, oops. Okay, carbon monoxide ratio is going to be 3 to 1. Okay, carbon monoxide is 2801. Okay, so we're going to so we've used 6.83 grams of rust. Excuse me, of not rust, of carbon monoxide. Because we had excess carbon monoxide. Okay, that's the purpose of step 3. Step 4 is to how much is left over. Okay, so we started with 13. And we've used 683. So you have 6.17 grams excess. And is there a yield? No. And there could be another step if I ask for a percent yield. Okay, that's a typical intermediate limiting reactant stoichiometry problem. Yeah. What did we start with? Oh, we started with 20. Yes. Thank you for that. Good. Oh, I actually gave you the actual amount, 3.45. Okay, so if we were to find so step number 5 would be we have 340. Okay, so to find the percent yield, we put actual over theoretical. And the theoretical is 908. Actual is 345. So percent yield is 38. Now your test, instead of having this limiting reactant problem, you're going to have that as a take-home problem. Not this one, but one like it. And depending on the degree of difficulty of balancing the equation, I might balance it for you. I might not. It depends. Because I haven't made up the one yet. But I'm going to have some more single step stoichiometry problems for your in-class test. So basically, I would give you one given, not two givens. Okay. So that's the focal point of your studying, is on conversions, grams to moles, grams to number of particles, number of molecules, and secondly, the stoichiometry part. Okay. All right, that's what I wanted to cover today to finish out Unit 4. So